And this is a submission for CISC699. This is the final demo explaining how the problem was set and how the problem was answered at the end of the semester. So let's dive right in. So this is called Real Estate Market Pricing Application. Short, I like to call it the REMP, R-E-M-P. So I'm going to talk a little bit about the motivation. So the motivation of this project and the purpose of the project was to create an application that can be used by both realtors and customers that are looking and selling to buy properties in a neighborhood. So the initial data set was set in Chicago. The data is built off of real world scenarios and is being used to build a machine learning model that can provide a prediction statistic that can be used for future scenarios. So basically all of the data was in the past. All of the properties that were located on the map that you see, or the properties that were used to train this model, were real world scenarios. So building a model off it should be relatively accurate for future scenarios as well. And then what basically happened in Grad 695 is that we derived an algorithmic determination supported by linear regression, housed on TensorFlow analysis to kind of ballpark a number on a property for either a realtor or a buyer with predefined conditions pertaining to the property in question. All right, so the next section is the DevOps pipeline. So the first, I think, 3-4 weeks of this semester, I spent working on the DevOps pipeline. So I'm going to give an overview. So the pipeline is entirely built on AWS Cloud. So these are the features that were used in part of it. The first thing is AWS Code Build, and the other one is AWS Code Pipeline. And then we have EC2 Application Load Balancer, Fargate, and then Elastic Container Services. So the first thing that happened, the pipeline is kicked off by any changes on the GitHub repository. So once you have some GitHub changes, the pipeline gets activated, and it's partly made up of 3 different stages apart from testing. So the first thing is the code build. So whatever that was in the code, it gets pushed, gets built in as a Docker image, and then this Docker image is tagged and then pushed to ECR. And then after it gets pushed to ECR, it then deploys it to Fargate using a blue-green code deploy pipeline. So that the tool that is used here is AWS Code Deploy. And once we have a Fargate definition built, services can be spun off using ECS, Elastic Container Services, that uses Application Load Balancer to expose it to the internet. And also the document DB is also housed in the same virtual private cloud, so it is possible to connect to it using a firewall. So this is like the overall setup of the architecture, the pipeline for this project. So that once you commit code to the GitHub repository, everything else happens seamlessly. Next thing is systems design. So these are the requirements, the functional requirements, non-functional requirements, and then the performance requirements of this application. So let's go over the functional requirements first. It says the system shall provide a questionnaire to apply variables to ML model, and then it shall also receive user-generated commands, and then the system shall also display the results in a human-readable format. The system shall run machine learning models upon every startup of the application. The system shall receive inputs based on what machine learning algorithm to deploy. The non-functional requirements is that it's scalable and robust. Because it is done on Fargate, you can so easily spin up however many container the definitions you want, and basically have however many services on ECS running as you want. And then this should also handle exceptions gracefully, so the user should know if they created a property or not, or if they edited a property or not. So all kind of notifications are right there on the top of the screen, so that has been done. And then should be designed to be run on all popular OS environments. So because we're containerizing the app, it is possible to do this. So I would call this a cheat. And then the second one, the fourth one is a real world scenario because we're building a model off of a real world application software. And then a NoSQL environment. And then it'll be a web-based application that can be accessed via the internet. The performance requirements, as usual, it's 10 seconds to start up the app, 3 seconds for every API call. The deployment should be done at least within 5 minutes. Next up is we have specifications. I'm going to go through the high level of what the software that I'm using. The operating system that I built using is Mac OS Mojave, but then you can use whatever you want because it's basically container. Container can run anywhere. The backend programming language is Node.js. IDE that I've used is IntelliWebStorm, and then the front-end programming language is Angular 14. The security is default built-in security for Angular and Node.js, and then the server that I'm using is Node.js server that is running on Docker. The orchestration of all of the containers is done by Elastic Container Services provided by AWS, and then the images that I use to store is container ECR, which is kind of like Docker Hub but for AWS. And then the deployment style is blue-green deployment task sets. And then the building services is AWS Code Build. Everything is strung up and orchestrated using AWS Code Pipeline. The API testing is done using Postman-Newman cases, and the front-end testing is done using Ghost Inspector UI. And the hardware, the one that I used to build it is 2.3 gigahertz Intel Core i5, and then the load balancer is the EC2 application load balancer. The Fargate task size is 512 megabytes. The task CPU is contained of 256 units, and then the database is MongoDB. I want to talk a little bit about the machine learning model. So the machine learning model is TensorFlow. TensorFlow is not. It might sound complicated, but at the end of the day, it's just a neural network. So it has a lot of different components strung up together, kind of like in a graph-like data structure, where each node is a tensor. The main driving theory behind this library is using neural networks, but sometimes it can also be either linear or poly regression. So for this model, I'm using linear regression. The basic data structure of TensorFlow is using tensor. Usually, the underlying data structure of a tensor is a multi-dimensional array, or in other words, matrices. Tensor can be identified as one of the following attributes, so it should either have one of the three, that is a rank, the unit of dimensionality of a tensor, the shape is the number of rows and columns in an identifiable matrix, and the type is the data type of predictors and response variables. And then the model parameters is just is how the cross-validation is done and things like that, but it's not super important. Just wanted to put it out there because if somebody wants to replicate it, they should be able to do it. So the type is TensorFlow, as explained already, and the value is sequential. Unit for loss function is 100. The activation is linear regression, as explained already. And then I'm setting it as 50 epochs. The validation split is 20%, 80%, 20% for test, 80% for training. And then the batch size is 50 for each epochs, and batch size should be the same. And then the loss function is mean squared error. So that's how it calibrates it itself, using the loss function, which is derived off of the MSE. So there are variable descriptions. All of the variables that you saw on the front end of the application is just listed here. So lot area in square feet, total basement feet is square feet, ground living area, and so on. All of this will be explained in the other video. And then the architecture of the application is, so first up is overall architecture. It should be pretty easy to understand. So the application has a predictor model, which is derived from the training data. And then there's a front-facing questionnaire, which talks to the predictor model. And the server is the one that facilitates this conversation between the front end and the predictor model. And every time a request is made, the predictor model spits out a value, which is then displayed on the front end. The detailed architecture, there are three components. One is the machine learning model that we talked about, and then the back end and front end. So the back end is Express.js coupled with Node.js. So all of the routes is exposed using Express.js. And then the front end should be very typical, as in any traditional contemporary front-facing languages like React and Angular. So it has views, MVVM style, model view, view model, and then it has the DAO layer, and then all of the REST services and configurations are served up in the promise-based HTTP services. And then there is the user dashboard, which is HTML and CSS. And then the front end architecture should be pretty similar to anybody that has used React and Angular. So we have all of these services that are served up not by Axios, but by the observables that come with Angular. And then each of the module has components, service, HTML, CSS, and TypeScript. So this is the setup of how these components are strung together and orchestrated inside the Angular application. Ethical and societal effect. So basically, the technical responsibility is that should come with most frameworks to avoid data leaks. So customers are going to entrust this application with a bunch of data, personal data, or sometimes sensitive data. All of that should be protected. Shall value the privacy of customers and shall not share the information across other platforms. Basically, the application will not sell data for profit. The software shall protect passwords of the consumers with hashing. The software shall not sell customer data to third party. The software shall be governed by OpenAM and OpenConnect, which is the most secure SSL certificate issuer that is out there right now. The software shall be encrypted by using TSL certification, and the certificate issuer would be somebody valid like Google. The crux of the application is a machine learning model. So we need to give careful thought so as to ensure that there's no racial, gender, and sexual orientation bias into the input data modeling. And then the stakeholder responsibility is that whenever something wrong happens, we need to let the stakeholders and customers know that something has happened. So third-party breaches and dependency tree security updates shall be provided to consumers as and when necessary. Contribution to code shall be welcome, but with scrutiny and analysis that the absorbed code poses no threat and/or risk to stakeholders and consumers of the application. SQL injections will be dealt with seriously. A team of professionals shall monitor the authorization requests and ensure proper flow of data. A tool to report other consumers of the application shall be set up, and the report shall be carefully examined for possible violations of community principles and guidelines. I want to conclude saying that this is a very relevant problem that is being faced by the community today. I would like to conclude that there are other modifications to the better of the product should be done before it could be ready to face real-world challenges. The basics of the functionality of the project is here presented in this report. Companies such as Zillow have already started tapping into artificial intelligence to predict an estimate of houses. So I conclude that I argue that there is a relevant problem that needs careful consideration and assumption which will need to be answered. Thank you.